Okay, a quick video on how you might go about using GeoGebra to construct a figure in our study of geometry that might be similar to something you'd be asked to do for your GeoGebra portfolio. Okay, so I thought maybe the easiest way to explain this would be to choose a book problem. And so what I'm going to do is I'm going to choose the book problem um, 1D number 4. So I guess it's this one. Prove that a parallelogram having perpendicular diagonals is a rhombus. Okay, so I guess if we were going to go to GeoGebra, what we would do is we would construct a figure that's always a parallelogram and then allow the user, and then construct its diagonals and then allow the user to manipulate the parallelogram so that they could investigate what happens when they make the diagonals perpendicular. So that's the way I think I'm going to go about doing this one. There are different ways, of course, that you could investigate a proposition, but I think that would be the easiest way to sort of make sense of this one. Okay, so I'm going to go ahead and step out and pop up my GeoGebra. There it is. So I guess the first thing I want to do is I want to construct a parallelogram. So this is a quadrilateral that maintains the properties of a parallelogram, which is, of course, that opposite sides are parallel. Okay, so I think the easiest way to do it is to start with one side. So I guess I'll start with a segment like this, and that'll be a side of my parallelogram. And then what I want to do is construct a parallel line. So I'll go to the parallel line tool, and what it'll say is that you have to select a parallel line and a point. So I can select a parallel line here and a point, but the point's going to have to be up here to make it look like a parallelogram. So I guess I need a point before I can use the parallel line tool. I'll put the point right there. Then I'll go to the parallel line tool and I'll select this line and that point, and I get a parallel line. So that's kind of nice. I guess you can kind of think of, well, we've got two sides of the parallelogram, and the third side I'm close to having it. But I think if I just did the parallel to this side through that point, we would be done. So I'll again use the parallel line tool. I'll click on this line because this is the one I want to be parallel to, but I want to go through that point. And I get two lines that now intersect in a point. I can either just sort of hover over that and construct the point, or another way you can do that, if you'd like to use the intersect tool, you can click on this line and this line and it'll find their intersection for you. Okay, so we have a parallelogram, but we got kind of some extra lines too that we don't really need, these two lines that we used in the construction protocol. So I think what I'll do is I'll just get rid of those two, but not the point that is defined by those two lines. And now I'll go ahead and construct my polygon. In fact, I'll get rid of these segments too and construct my polygon. There it is. 1, 2, 3, 4, 5. GeoGebra has kind of a coloring protocol for constructions. The blue points, when you first construct them, those are all free points, whereas the black point is depends on the other 2 points. So it would depend on these 3 points. And of course, that's because of the construction protocol of parallels opposite sides. But now would be a good time to check to see if our construction passes the drag test, and it sure looks pretty good. Right now it looks like what we have is a parallelogram, general parallelogram. Kind of a fun thing to think about is that, we can play around with this to find out that, oh yeah, indeed, it looks like squares are parallelograms. I could do something like this and find out, well, what about rhombi? So can I make all, yeah, it seems like, well, that looks like a square. So that looks like, yeah, down 2 over 3 everywhere. So these four sides are the same. So this must be a rhombus, and rhombus are parallelograms too. So we've got the parallelogram. What we'd like to do now is construct the diagonals. There's one diagonal. I'll construct the other diagonal. I'll go ahead and construct the intersection of the two diagonals. Oops. Oh, there it went. The reason I did that is because now that'll allow me to measure the angle. So I'll measure the angle from here to here to there. Um, and I can see the angle of this, I guess, at which the two diagonals of this parallelogram intersect is about 80. There is a 90 degree angle. So once again, let's just go back and remind ourselves what we're trying to prove or show. We're trying to prove that the parallelogram having perpendicular diagonals is a rhombus. So to ensure that it's a rhombus, I mean, we can look in a couple different places. One of the places we can look is right over here to see that indeed all four of the lengths of sides is 3.61. Or we could use the measurement tool to to measure the distance. So I could, measure that distance, that distance, that distance, and this distance, and find out that those distances are the same. But here's what's kind of interesting is just as soon as that angle diverges from 90, the parallelogram ceases to be a rhombus, right? So this is, I guess, what I would think would be a perfectly good, let's just play around with it a little bit more. So there we go. Now we're back to a 90 degree intersection for the two diagonals, and it seems like we're a rhombus there. Um, if I maintain that 90 degree and just sort of push this up and down, I can see that every time this is 90 degrees, these four sides are equal in length. If I diverge just a little bit, right, from 90 degrees, then the four sides cease to be equal in measure. But it's still a parallelogram, we know, because this side is parallel to that side by construction. So it does indeed seem that the statement of the theorem is correct, that anytime the diagonals of a parallelogram intersect at a 90 degree angle, then the sides of the parallelogram are all equal in length. So it seems that we should be able to prove this as a statement that's true always. Kind of fun to just play around with this just to see. Keep sort of playing here. Maybe I would leave a little bit of a note to a user here that says what to do with the diagram. So I'll go ahead and use the text tool and type up a little bit of instructions. Manipulate points A, B, C, and D this thing you have to kind of use a return to make it narrow enough to post. So manipulate points A, B, C, and D to, what do we want to say, to create perpendicular diagonals. You will notice that when the diagonals are perpendicular, the lengths of the sides of the parallelogram are always equal. I think that's probably good enough. So you could do something like that and leave a note to the user. And I think this is a pretty good example of kind of what I would expect. I would hope to open something up that would look like this. Once you have everything done, you of course could close the algebra view so that it just becomes just this little page. And smaller like this. So something like this is what I would hope to see when I open up the links to your GeoGebra portfolio items. So I hope that gives you a little bit of a sense of what I'd be expecting in terms of a construction that would support conjecture, or I guess a hypothesis that you're getting out of the text. All right, I'll stop there.